So we were speaking about a simple model for neurons, the McCulloch-Pitt or MCP model. So let's try to put this into action. But first I want to underline one thing, that at this point of the description, these are not biological neurons. So these are not implemented as pieces of biological tissues, chemicals, whatever. It's just mathematics. So it's a way of describing what happens. If you ask me, how can we make a weight variable here inside the neuron? I have no idea. How can we how can we be sure that this x variable can be either 0 or of 1? It's an assumption at this time. So it's just a simplification of what can be probably maybe implemented by nature, let's say. But now we just speak about an abstract representation from the functional point of view. So we can do circuits basically with all those elements. So let's analyze this case. So now we have a summating node where we take an input x, which can be either 0 or 1. The weight corresponding to this we define to be w equals -1. And here we have another input with a constant value 1, so a pulse of trains which is always like 1 1 1 1 1 1 1 1 1 1 1 like this. So we call this a spontaneous activity, and a weight equal to 1 corresponding to this input. So let's try to calculate what is the output of this summating node here. We do this here aside. Okay, so the summating node is a coefficient which is 1, this w, multiplied by the input which is 1. So 1 by 1 makes 1 all the time. Then we have to add the contribute to the second input, which we called x. So it's x multiplied -1. So here we have minus x. And x can be either 0 or 1. So this thing can be 1 when x equals 0, or 0 when x equals 1. And if you look at this, it's the truth table of a NOT gate. So if you put x and you call y the output, then in order to, let's say, complete this paradigm, we need a threshold. Let's put this threshold at 0.5. So if x is smaller than 0.5, like when x is 0, then the output is 1. And if s is bigger than 0.5, then so when s is 1, then the output is 1. And then we have exactly the truth table of a NOT gate. So this neuron here, the way we define it with these two inputs and those two weights and this threshold, is implementing a logic function, a NOT gate. So let's try to do another one, but I guess that you understood the trick. So we need to compute the summation here according to this model. So now we have two inputs, x1, x2. They both have a threshold of 0.5. So we cleverly designed this way. And now let's try to demonstrate that this thing with a threshold of 0.25 this time is a OR gate. So we have our variable s, and this would be 0.5 x1 plus 0.5 x2. So x1 and x2 are the inputs of this black box and y is the output. Okay, so then we have to write all possible cases. So let's say x1, x2, and let's put a column for s. So we have to remember that the inputs are binary, the spike is there or it's not there. So we have 4 possibilities like this. So the first one is 0.5 multiplied 0 plus 0.5 multiplied 0 and makes s equal 0. Then we have 0.5 multiplied 0 plus 0.5 multiplied 1, which is 0.5 and similarly here. And then we have 0.5 multiplied 1 plus 0.5 multiplied 1, which makes 1. So now you see that if I put a threshold, for instance, at a level 0.25, let's say above 0, but below 0.5, then with that threshold, if I consider the output, then here the threshold is below that number, sorry, the value of s is below that number of thresholds, so the output is 0, and here is 1. And so we demonstrated that this guy is a OR gate. So let's try to do the last one. So I delete this stuff. So now we calculate this one. Again, we have to write all possible cases. So let's write the equation first. So our intermediate summation variable out of this summation node, now this time, okay, it's the same. So it's 0.5 x1 plus 0.5 x2. And now let's write all the possibilities for our inputs. Again, 0, 0, 0, 1, 1, 0, 1, 1. So the output s now is this by this plus this by this and makes 0 in this case. Then again it's exactly the same thing, so it's 0.5, 0.5 and 1. But now what is different is this, the threshold. So now in this subsequent stage of processing of this signal, we choose to go for a threshold of 0.75. So let's calculate the variable y according to this new threshold. So if it is below 0.75, the output stays at 0, but if it's above 0.75, the variable y goes at 1. And so this way we implemented a AND gate. So you see, now we don't have those transistors, the pull up and pull down networks, we have a summating node and a threshold, and we are able to implement logic gates. So those population of neurons, a population of neurons of those three types will be able to build a tablet like this, a microprocessor, because it can implement digital electronics in a form of Boolean logic, the one that we studied for digital circuit. So,
sorry, Professor, can I make a question?
yes.
I want to know if it's possible to change the threshold, and in order to change from a not to an or like, are they interchangeable?
Yes, in fact, this is the beauty of this thing. So I prepared a little thing here. So imagine you have a, oops. Imagine you have a knob like this. I don't know if you can see it, but so let's say that we put the threshold at 0.25, like this. So if you see, for instance, the only thing that makes this circuit to be an OR gate or an AND gate is just the level of threshold. So all the rest is the same. So the building blocks are the same. The weight are the same. The only thing that changes is the threshold. So it means that if you put it at 0.25, you have an OR gate. But if you increase it and you go to 0.75, you have an AND gate. And the question is, and if I modulate this threshold in between, what do I have? Of course it's possible to do this. And then we will discover that we will go beyond the Boolean logic. So those circuits, the neural circuits like this one, in this very, very simple model of McCulloch's and Pitts, already is able to uncover the fact that neural networks, the digital electronics, the way we invented, the way we are using it, is just a very little particular subset of what a neural network can be able to do. So if you change the threshold, now we don't study these intermediate cases, but you can imagine you can have also more complicated cases, interconnected things. So if you change the threshold and weights, of course this thing will compute something. Now it's hard to say what, because we can't easily recognize the result in terms of Boolean logic, but it will produce something that will depend on the input and the weights and the thresholds. So this paradigm can compute much more than what let's say a digital computer can, because it has more degrees of freedom. So with little things we can compute a very complicated operation that we probably will be able to explain and implement also, let's say, with the normal computing paradigm like the CPU. But probably with that paradigm we need more components, more things. So here it's a very compact way of doing computation. So we might expect, so this is the ultimate message, that if we modify the weights and the threshold with the same hardware, we can compute much many things that respect to what we can do with computers. So I hope that this can somehow answer, even if not completely, your question. So neural networks are more powerful. That's basically the end of the story. And computers is just a little piece of neural networks. And this makes the story very interesting for those who are interested in going into this field. This is just an very naive introduction. Another thing that we can notice is a different description, which is called state machines.